This lecture is about torque. And we define torque as the capability of rotating objects about or around a fixed axis. And so this could be also described as the multiplication of force and the shortest distance between the application of force and that fixed axis, or the radius. So torque is equal to F cross R, which is equal to FR sine theta. And torque looks really, really similar to work. Remember, work is just FD sine theta, but work occurs in a straight line. So work is talking about kind of a two-dimensional idea of pushing a block forward or lifting a book or something like that, whereas torque, we're talking about rotation specifically. And because our force has a vector quantity, our force has a magnitude and a direction, torque is also a vector, which means that it has a direction. So when we describe torque, we talk about clockwise or counterclockwise. So clockwise or counterclockwise when we're talking about the direction of torque. So the direction of rotation around a fixed axis. When we're talking about clockwise or counterclockwise, we also talk about positive or negative. So clockwise would be the positive direction, counterclockwise negative. And that's kind of a convention that you probably think about normally, because our experience is anything that goes to the right or anything that circles to the right is positive, whereas anything to the left, anything that circles to the left is negative. So a lot of times when we talk about torque, we use examples like a door swinging open or closed, or a wrench applying a force to a bolt, or anything like that. So if we were to have a door, and here's its hinge here, and here's the wall here. Here's the wall. And we applied a force this way, it would cause the door to swing counterclockwise or in the negative direction, and we could say that it's swinging open, and then if we applied a force the other direction, it would swing clockwise or in the positive direction, and maybe it would be swinging closed. So let's do an example of an irregularly shaped object. So here is our point of rotation. Our object is a triangle. We have a force here, F3 is 6. Force 1 is 5. And we have force 2, 4 newtons, and we have 2, 2, 3, and 5 are our lengths here. So this 2 is saying that from the bottom here is 2, and then the distance to the top is also 2. So we're going to answer two different questions here. First is to find each individual torque, and then find the total. So our first question is, if each of the forces were acting individually, so without the others, and then if all of them were acting at the same time, what would happen? So let's talk about the torque for force 1. That would be F1, r1 sine theta. And because our theta is 0, then sine theta goes to 0. So our whole term, despite what these two things are, despite this being 5 newtons and this being 4 meters, would go to 0. So our torque from force 1 is 0. Our torque from force 2 is F2 R2 sine theta. That's equal to 4 newtons times 2 meters times sine of 90, which is equal to 1. So that gives us 8 Newton, I'll erase that, Newton meters. And our torque from force 3 is equal to F3R3 sine theta. And that's equal to 6 newtons times 4 meters, because we're just going to talk about this distance here. Despite how far out the force is occurring, we're just talking about the distance from the axis of rotation times sine theta, which is 90, which is 1, gives us 6 times 4 is 24 Newton meters. But force 3 and force 2 are acting in opposite directions, and if we are using our convention saying that anything going this way is positive and anything going this way is negative, then we'd have to say that force 2 is negative and force 3 is positive. So therefore, our total is 24 minus 8 is 16 Newton meters in the clockwise direction.